So just going to do some of the homework from section 2.1 to get us, comfortable using the power rule and just let me just jump into it. So the first problem, my first even problem, wants me to find the derivative of a function written as g of x. So I should probably write my derivative with the g prime of x symbol. And I should probably not show any work. I should just write the answer down. But using the power rule properly, the derivative of the 2x to the fifth term, I'm going to multiply the exponent 5 by the coefficient 2 and get 5 times 2. And I'm going to lower the exponent by 1. Ultimately, for this first term, I should have done this in my head and written the first part of my answer as 10x to the fourth. And then for the next term, I'm going to bring down the minus sign. I'm going to multiply the exponent of 3 times the coefficient of 5, and I'm going to lower the exponent by 1. Again, this I can do in my head as well. This is going to be minus 15x squared. And then the last two terms, I'm going to be ultra lazy. The 3x is the first power term, and the derivative of any first power term is just its coefficient. The last term is a constant. The 4 is a constant. The derivative of any constant is 0. My answer to question 2 is 10x to the fourth minus 15x squared plus 3. And I don't think that factors, but even if it did, at this point, we're not going to be factoring our derivatives. 4 is a simple example as well. I'm going to do the derivative of each term, get the derivative, which I could write in the dy dx form, or to the left of the equal sign, I can write y prime. I usually write this prime, it's just easier to write. And let me do this in my head. First term, I go 3 times 6 is 18. For its derivative, its coefficient is going to be 18. Lower the exponent by 1. 3 minus 1 is 2. Middle term, really this is 1x squared. When I do its derivative, I multiply 2 times 1 and get a positive 2 for the coefficient. The exponent on the x should be 1 because 2 minus 1 is 1. When I write my answer, I'll suppress that 1. And then the derivative of the last term, because it's a constant, its derivative is 0. Best answer that I probably could have written just directly is 18x squared plus 2x. Had a mistake down there. For the problem 6, let me write dy dx as opposed to y prime, but they're equally good ways to represent the derivative. First term, I'm going to go 2 times 12 and get 24. I'm going to lower the exponent by 1 and get x to the first. Second term is a first power term. Its derivative is just its coefficient. Last term is a constant. Its derivative is 0. So the derivative of minus 3x is minus 3. The derivative of minus 4 is 0. Minus 3x I call a first power term because the exponent on the x is 1. The derivative of any first power term is its coefficient. The last term I call a constant because it doesn't have an x. The derivative of any constant is 0. For an answer to number 6, either with a dy dx preceding an equal sign or a y prime preceding an equal sign, but 24x minus 3 for my answer. 7 and 8 both want me to find the derivative of a constant. I have a new function name. Doesn't matter what the function name. If I put the little prime symbol with the function notation, that indicates I'm finding a derivative. And in this case, I'm finding a derivative of a constant. Derivatives of constants are 0. My answer to problem 8 is just 0. And there's no real work to show for it. Well, I could show some work, but I showed that work in the theory, and I don't want to get into the theory here. I just want to do the applications efficiently, and the derivative of a constant is 0. The next chunk of problems are going to need to be rewritten before I can make the derivative happen. And in problem 10, I need to make the radical have a fraction exponent. And in problem 10, this is really 12 times the cube root of x to the first. And to make a radical into a fraction exponent, I write the radicand, in this case the x to the first power, and I make the index the denominator of the x of the fraction exponent. Radicals turn into fraction exponents. Now I'm going to find my derivative by multiplying the exponent by the coefficient, and I'm going to lower the exponent by 1, but instead of subtracting 1, the 1 that I might subtract, I'm going to think of that as 1 over 1, and instead of subtracting 1, I'm going to take the 1 and write it as 3 over 3. First of all, the 1 that I might subtract is equivalent to subtracting 1 over 1. That's the fraction version of 1. Because the fraction in the numerator has a denominator of 3, instead of subtracting 1, I'm going to subtract a fraction with a denominator of 3 that's equal to 1, and 3 over 3 is equal to 1. So this is my version of subtracting 1 for this problem. And then in terms of simplifying, this 1/3 cancels with the 12. The 3 becomes a 1, so I don't get a fraction as my coefficient. The 12 turns into a 4. I'm left now with the derivative is 4 times x, and when I subtract the exponents, I get 1/3 minus 3/3, which is negative 2/3. I should make negative exponents into fractions by creating a fraction. And the denominator of the fraction is just going to be the term with the negative exponent. The coefficient's going to stay in the numerator. And then I should make radicals out of fraction exponents. So the radical version of x to the 2/3 power, this is going to become the index, and the x squared is going to become the radicand. So I'm going to get the cubed root of x squared for the best version of my answer. If it was a test question and you got to here and it was a 6-point question, this will get you 5 points, and then writing it in a nice form is going to get you an extra point. Twelve is another radical, so I need to make it have a fraction exponent before I could use the power rule. So let me emphasize number 12 is really 14 times the second root of x to the first. In a square root problem, the index is implied 2, but not written. When an x has an exponent of 1, it's implied, but not written. This is not taking the derivative, so I haven't written a little prime. And even on my next step, I'm just rewriting the problem to put it in a form that's ready for the derivative. That's not taking a derivative, so I'm not writing a prime. So the fraction exponent of the square root of x to the first is x to the 1/2. Now I'm going to take the derivative, so I'm going to write my little derivative symbol. I'm going to multiply the exponent of 1/2 times the coefficient of 15, and I'm going to subtract 1 from the exponent. And when the exponent's a fraction, I always subtract the fraction version of 1 that is appropriate. And here, instead of subtracting 1 as just the number 1, I'm going to subtract 1 written as 2 over 2, because 2 over 2 is equal to 1, and it's more useful for the algebra I need to do. Now I'm going to cancel the 14 with the 2. The 2 is going to become a 1, so I won't have a fraction anymore. The 14 is going to become a 7. So my derivative is going to be 7x, and then 1/2 minus 2/2. I subtract the 1 minus 2 and get negative 1, and I leave the denominator. So the derivative is 7x to the negative 1/2. I'm going to make my negative exponent positive by creating a fraction with a 7 in the numerator. And then I'm going to turn the fraction exponent into a radical by making the denominator the index and everything else the radicand. And I can suppress the 2 and suppress the 1. Best answer for number 11 is the derivative is 7 over the square root of x. The next few problems have fraction exponents. I usually write my answers as radicals. Definitely if the problem starts with radical notation, I should write my answers with radicals. If a problem starts with a fraction exponent, then maybe we're okay with the fraction exponent, but I'm going to say I'm going to make all fraction exponents into radicals until it gets too hard for me to do, and I'm not sure that that's going to happen today. So I'm going to take the derivative by multiplying the exponent by the coefficient. This 1/2 is supposed to be an exponent. It doesn't hardly look like an exponent, but it doesn't look raised, but it is. It's just somehow what Word did to me. Multiply the exponent by the coefficient, lower the exponent by 1, but do the 2/2 version of 1. Cancel the 10 and the 2 and the 10. The 2 becomes 1, the 10 becomes 5. This is going to give me the derivative is 5x to the negative 1/2. Now I'm going to create a fraction to make the exponent positive. Get the derivative, our g prime of x is 5 over x to the 1/2. And now I'm going to make the radical from the fraction exponent. That's the second root of x to the first. I can suppress the 2 and suppress the exponent of 1 and it would have the same meaning. This is the best answer for 14. In 16, I need to think of there being an exponent, a coefficient of 1. I need to think of this as f of x equals 1 times x to the 1/5 power when I go to do my derivative. To do the derivative, I'm going to multiply the coefficient of 1/5 times the implied coefficient of the exponent of 1/5 times the implied coefficient of 1. I'm going to lower the exponent by 1, but the appropriate version of 1 for this fraction exponent, so I'm going to subtract 5/5. And this is going to give me the derivative is 1/5 times x to the negative 4/5. I don't know how much algebra to show here. I would just generally just slickly write this negative exponent next to the 5 in the denominator, but technically this negative exponent can be written as 1 over x to the 4/5 power. Anytime I have a negative exponent, I can rewrite it with a positive exponent if I slip a 1 in the numerator, so that this derivative is really 1 over 5x to the 4/5 power. And now I can make my fraction exponent into a radical. The 5 doesn't apply to the radical because it doesn't have a fraction exponent. When I go to write the radical version of this coefficient of 5 is going to be out front. Then I'm going to write the radical. The denominator of the fraction exponent becomes the index, and the rest, the x to the 4th, becomes the radicand. That's the best answer for 16. The next few problems I'm going to rewrite with negative exponents to make it so I could use the power rule. In problem 18, I'm going to rewrite the problem without the fraction. I'm going to write it as 5 times x to the negative 3 power. And then I'm going to take the derivative. I could either write y prime or I could write dy dx. I'm going to multiply the negative 3 times 5 and get negative 15. And then I'm going to subtract 1 from the exponent. And negative 3 minus 1, because both those numbers are negative, is going to give me negative 4. I'll add the numbers and make them negative. So this is going to give me the derivative is negative 15x to the negative 4th. We usually don't leave negative exponents or fraction exponents in our answers, so I'm going to make this into that by creating a fraction, moving the x down to the denominator of the fraction and leaving the negative 15 up in the numerator. And when I move the x down, it gets a positive exponent. For 20, I need to think of this as negative 5 over x to the 1st power, so that when I rewrite it with the negative exponent, I know the appropriate exponent. This rewrite should be negative 5 times x to the negative 1 power. Haven't written the derivative symbol yet because I haven't done the trick of multiplying the exponent by the coefficient. Now I'm going to do that. I'm going to write the derivative symbol. I'm going to go negative 1 times negative 5 and get positive 5. And for my exponent, I'm going to subtract 1. And negative 1 minus 1 is negative 2. So my derivative is going to be 5x to the negative 2 power. I'm going to make my negative exponent positive by creating a fraction. I'm going to leave the 5 in the numerator of that fraction, and the x to the negative 2, I'm going to make an x squared in the denominator of that fraction. At this point in our class, we don't know how to do derivatives if there's multiplication, so I need to get rid of the multiplication. In section 2.2, we learn how to find a derivative without getting rid of the multiplication. But in problem 22, I'm going to need to rewrite this problem by foiling. I need to go firsts, outers, inners, and lasts. And I'm going to get y equals to 15x squared minus 24x minus 20x, and then minus 4 times minus 8 is plus 32. I'm going to combine these minus 24 and minus 4x and get a rewrite of the problem that's not the derivative, but this is a form that's useful for the derivative, as 15x squared minus 44x plus 32. Now I can take the derivative using whichever notation that I care for. First term, I'm going to go 15 times 2 times 15 and get 30. Lower the exponent to 1. Middle term's a first power term, so its derivative is just its coefficient. Last term's a constant, its derivative is 0. So for an answer, the derivative is 30x minus 44, whether you use that symbol or that symbol to precede your derivative in your answer. I suggested skipping 23 and 24. This is just really a foiling problem, and 23 looks a little easier than 24 anyways. Let's move on to 26. I can't at this point do the derivative when there's multiplication. I need to get rid of the multiplication. In problem 26, there's a lot of multiplications I need to do to rewrite the problem. In problem 26, I need to take the 3x squared in the left parentheses, multiply it by the 4x and the 1 in the right parentheses as I'm trying to rewrite this problem so it doesn't have multiplication. I need to take the 6x in the left parentheses, multiply it by the 4x and the 1 in the right parentheses to help get rid of the multiplication. And I need to take the negative 2 in the left parentheses, multiply it by the 4x, and multiply it by the 1 in the right parentheses to clear the multiplication. So this problem rewrites as the first multiplication gives me 12x cubed, second multiplication plus 3x squared, third multiplication plus 24x squared, fourth multiplication plus 6x, fifth multiplication minus 8x, last multiplication minus 2. I have like terms that I should combine. So I've not taken a derivative yet, I'm just rewriting it. And the rewrite of this is going to be 12x cubed plus 27x squared minus 2x minus 2. Now I can take the derivative term by term. First term I go 3 times 12 and get 36. Lower the exponent by 1. Second term I go 2 times 27 is 54. Lower the exponent by 1 and get 1, which I normally wouldn't write. The fourth term is a first power term. The derivative of any first power term is its coefficient. Last term is a constant. The derivative of any constant is 0. So that's the derivative. It can be cleaned up to look like 36x squared plus 54x minus 2. I suggested skipping 27 and 28, but you're free to do 27 if you care to. I'm going to do 30 and get rid of the multiplication by doing 4x cubed times 3x squared and 4x cubed times 7x and 4x cubed times minus 5. So the rewrite of this problem is going to be 12x to the fifth, that's what the first multiplication simplifies to, plus 28x to the fourth, that's what I get for the second multiplication, minus 20x cubed. So I'm doing basic intermediate algebra without explaining, so hopefully your algebra skills are good enough that you can handle what I did there. Now I'm going to take the derivative, and you'll notice I'm not really factoring my derivatives at this point because I'm not doing anything with them. So I'm going to first term, I'm going to go 5 times 12, and that's going to be 60. I'm going to lower the exponent to 4. And then 4 times 28, I'd normally use a calculator for that, but I'm assuming I did this correct when I wrote this key. So it's going to be 112. Lower the exponent by 1 and get an x cubed. Last multiplication, 3 times minus 20 is minus 60, and lower the exponent by 1. If you wanted to, you can pull out a common factor of x squared, oh, maybe even like 4x squared. I can't quite tell how big of a number I can pull out of there. But for now, let's just get the derivatives and worry about working with the derivatives later. You can do 31 if you care to, clear the multiplication and do the derivative. Just trying to keep the videos at a sane length, and I don't know that I need to do every problem, and nor do you need to do every problem unless you feel you need the practice. If you feel you need more practice, do this problem. The next few problems are division problems, and we will learn a rule to be able to not get rid of the division and find the derivative in section 2.2, but we don't have that rule yet. So I need to, for each of the next 3 or 4 problems, rewrite the problems so that they're suitable for a derivative. Oh, this answer is not going to be right down here. You can't see it, that's good. So now the rewrite of this is going to be, first term is going to be 2x squared. Second term is going to be 3x. Third term is going to be 5 over x. The 10 and the 2 cancels out to be a 5, but the x doesn't go away. So let me rewrite this now as 2x squared plus 3x. And I'm going to write this last term as 5x to the negative 1 power. Now I'm ready to take my derivatives. So now I'm going to write my derivative symbol. First term, I'm going to go 2 times 2 and get 4. Lower the exponent and get an x to the first. Second term's a first power term, and first power terms have derivatives of their coefficients. Last term, minus 1 times 5 is minus 5. I'm going to lower the exponent by 1, and negative 1 minus 1 is going to give me negative 2. I'm going to make that negative exponent positive and call this an answer. So I'm going to say my derivative is 4x plus 3 minus 5 over x squared. It maybe looks weird having that x term written last, but I'll live with it. Do the same for 36. I'm going to do the same for 38. I'm going to rewrite the problem. I don't know how to take the derivatives when a problem's written as a fraction with an x in the denominator just yet. So I'm going to rewrite each of the fractions in this section by taking each term in the numerator, writing it separately over the denominator, and then I'm going to reduce the fractions. The first term reduces to x, the last term reduces to 4. That first term has an implied coefficient of 1. When I go to take the derivative, it's double shortcut. The first term is a first power term. The derivative of any first power term is its coefficient. The last term is a constant. The derivative of any constant is 0. And number 36, the derivative is just going to be 1. (38), same deal. I'm just going to rewrite this as multiple fractions. I'm going to say the fraction can be rewritten as 25x squared over 5 plus 5x over 5 plus 15 over 5. This is going to give me a rewrite of first fraction reduces to 5x squared. Second fraction reduces to x. I might write 1x. Last fraction reduces to 3. Now I'm going to find my derivative. First, I'm going to go 2 times 5 and get 10. Lower the exponent by 1 and get 10x to the first. Middle term's a first power term, so its derivative is its coefficient of 1. Last term's a constant, its derivative is 0. For an answer, 10x plus 1 for the derivative is the best answer for this point. You can do 39 if you care to, but I suggested to skip it. And we just have a couple problems left about finding slopes and finding equations of tangent lines, and maybe we'll just do 2 of these. So each one of the problems between 41 and 44 has a part A and a part B. Part A wants me to find the slope of a tangent line at some point, some value of x. Part B wants me to find the equation of the tangent line. To do part A, to find the slope of the tangent line, we're going to find the derivative and plug the value of x in. That's how I get slopes of tangent lines. this case, I'm going to plug x equals 3 into the derivative. So real quick derivative in problem 42. The first 2x squared has a derivative of 4x, just 2 times 2 for the coefficient and lower the exponent to 1. The minus 6x has a derivative of minus 6. The minus 2 has a derivative of 0. My slope of my tangent line, I'm going to get by taking the value of x that's given, which is 3, and I'm going to plug it in for x. So my slope is going to be 12 minus 6. My answer to part A for number 42, the slope of the tangent line is 6. For part B, I know a slope, which is 6, and I know part of a point, which is 3 comma something. In order to be able to find the equation of the line that I'm asked to find, I need to get the y-coordinate of the point. And to get the y-coordinate of the point, I'm just going to take the given value and plug it into the original function. So I'm going to get y equals, and then 2 times 3 squared minus 6 times 3 minus 2. This is dumb to do without a calculator. I think I get minus 2. That's assuming I did that math okay. In my head, you should use a calculator. Now that I have both a point and a slope, I'm going to use the y minus y1 equals m times x minus x1 formula. Specifically, I'm going to go y minus the y-coordinate of the point, which is y minus negative 2, equals the slope, which is 6, times x minus the x-coordinate of the point, which is the given 3. This is going to give me y plus 2, the double negative on the left side becomes a plus, equals 6x minus 18, and then minus 2, and the equation of the line I'm searching for is y equals 6x minus 20, because of the 18 and the 2 have the same sign. And so I add and keep the signs negative. Oh, this is a good problem. For 46, it talks about horizontal lines. And this is a big deal. It comes up a lot in our class. I should have done something about this in the beginning, but I didn't. I have to know that all horizontal lines have a slope of 0. It comes up a lot in our class. So all horizontal lines have a slope of m equal to 0. So in part A, where it says find the values of x where the tangent line is equal to 0, it means to find the values of x that if I plug them into the derivative, I get 0. To do part 46a, we're going to find the derivative and set it equal to 0. And I'll show you what's going on here after I get the algebra done. So the derivative in 46, I go 2 times 2 is 4, lower the exponent by 1 and get 4x. That term minus 8x has a derivative of minus 8. The plus 7 has a derivative of 0. When I take the derivative and set it equal to 0, that's setting the slope equal to 0, because this is slope equal to 0, and that's what I want because horizontal lines have 0 slopes. This gives me 4x equals to 8, and when I divide by 4, I get x equal to 2. The answer to part A is x equal to 2. I say when x equal to 2, the tangent line has a 0 slope. And how can I show that? This is not necessary, but if I take the value that I just computed and I plug it in for x into the derivative, which gives me the slope of the tangent line, I get the slope of the tangent line as f prime of 2 is 4 times 2 minus 8. It's 8 minus 8, which is 0. So when x equal to 2, the slope of the tangent line is 0, and lines that have 0 slopes are horizontal. So when we're asked a dozen times in our class to find all values of x where the tangent line is horizontal, you find the derivative and you set it equal to 0. Part B wants me to find the equation of the tangent line. And to find an equation of any line, I need a point and I need a slope. The algebra in part A gives me the x-coordinate of the point. My understanding that horizontal lines have a slope of 0 gives me the slope. So the slope comes from the fact that I'm finding the equation of a horizontal line. The x-coordinate of the point came from my algebra. I need to get the y-coordinate of my point. To get the y-coordinate of my point, I'm going to go 2 times 2 squared minus 8 times 2 plus 7. This is going to be 2 times 4, which is 8, minus 16 plus 7. I believe that comes out to -1. If I've done a lot of these, I already know the answer is going to be y equals to -1 because horizontal lines only have y's in their equations. They don't have x's, and the y has to be -1. If I didn't know that, I can just do the algebra. Go y minus the y-coordinate of the point, which is y minus -1, equals m, which is 0, times x minus the x-coordinate of the point. Algebraically, the double negative on the left-hand side turns positive. Algebraically, anything times 0 is going to be 0. On the right-hand side, to clear the parentheses, I'd go 0 times x, which is 0, 0 times -2, which is 0. The whole right side will come out to 0. To finish this up, to get my equation, I would just subtract 1 from both sides, and I'd get the equation of the line as y equal to -1. We'll get a handful of these horizontal tangent lines before the section ends, and they come up, I'm pretty sure in chapter 3, and pretty sure they come up in chapter 4, so we'll get this again. If this wasn't quite clear, I'll try to make it more clear. But if I'm asked to find a value of x where the tangent line is horizontal, you find the derivative and you set it equal to 0, because horizontal lines have 0 slopes, and setting the derivative equal to a number, that's the number that you want the slope to be. In this case, I want the slope to be 0. Once I get the value of x, if I'm asked to find an equation of a tangent line, the value of x that I came out with in part A is the x-coordinate of the point. Because I'm finding the equation of a horizontal line, the slope by definition is 0. I do the algebra to find the y-coordinate, and I should be able to go right from the y-coordinate to the answer, because all horizontal lines only have y's, they don't have x's. I wouldn't have to do any of this algebra in purple. Once I got the y-coordinate of the point, I could have went directly to writing my answer, even though I don't have a tendency to do that. That's the end of 2.1. In 2.2, we're going to learn how to take derivatives when there's multiplication that is either hard to get rid of or I don't care to get rid of. And we're going to learn how to take derivatives when there's division that I can't get rid of or I don't care to get rid of.